All right, y'all. Today we're going to be talking about applications of exponential and logarithmic functions. So we've been talking about graphing exponential functions. We've been talking about graphing logarithmic functions. We've solved functions involving both exponents and logs. And now we're really going to kind of put all that together in our applications of exponentials and log functions and kind of how they're used in the real world, how we use them beyond just pre-calculus, and how we really put them into practice. So some of these formulas should be familiar. You should have used them in Algebra 2. So a lot of this is going to kind of be a repeat, but we're going to add in some skills a little bit more involving our logs, as well as just, continue to practice and build on these because, like I said, there's something you can actually use. But with that said, let's go and start with our first function. The first one we're going to talk about is our compound interest formula. So A is equal to P times 1 plus R over N raised to the power of NT. And to kind of talk about this equation, we want to talk about all the different variables that we have. So our first one is A. And A, as you can see, the whole equation is equal to A. A is really what we're trying to find. A is our final amount. Okay, and the next step on the other side, we have P. Everything is being multiplied by P. P is actually the principal. It does have a little bit of a fancy name. But really, in contrast to the final amount, the principal is the initial amount. Keeping on along, we have R. R does stand for rate. A lot of y'all probably already knew that one. And the big thing we need to be remembering about rate is that we do want to change it to a decimal. It's typically going to be given to you as a percentage. So if you see a rate of, let's say, 4%, okay, we would find that actual value of R by dividing 4 by 100, which of course would give us 0.04. We can also find that value of R by taking R4 and moving the decimal place over to the left twice and adding in that 0. So we have two different ways we can convert that R, but the big thing to remember is that we do always want to convert it by dividing by 100. 4% is not 0.4. 0.4 would be 40%, which is obviously a much different rate. Okay, the other variable that we have that's special to our compound interest formula is N, and N stands for the number of times interest is compounded per year. So with compound interest, you're actually compounding the interest. You're like multiplying it over and over again a certain number of times in the year to get this kind of compounded formula of the actual growth of the account. And so N is the variable that accounts for that compounding multiple times in a year. And then, of course, last T is the time. That's a pretty standard variable for all of us. Okay, and it's typically going to be expressed in years, probably about 99% of the time. Every once in a while, you'll see time change to a different variable, but it will be expressed in the problem. And we'll try to make it pretty clear for you. Last but not least, if the compounding is done continuously, sometimes you'll see this continuous compounding or continuous growth or something like that. We're actually going to use a different formula, and that is our A equals P times E to the RT, with E being the natural number, which we've talked about E before. Our natural log ln has a base of E, but E, the natural number, we use it. We call this equation the PERT equation because it spells PERT. But anytime you see that continuously, you use PERT instead of the standard compound interest formula. So let's look at number one. We're going to kind of talk this out as we plug it in. So we want to find the amount of a $500 investment after 8 years at 6% interest compounded. And we want to identify some of our key information in this problem that's going to be important to us. So we have $500 investment. That's definitely going to be our P. That's our starting amount. Then we have 8 years. 8 years is definitely our time that we are making this investment. And then last but not least, we have 6%. So our 6%, that's going to be our rate. And remember, we do want to convert it to a decimal. So R in this case would be equal to 0.06. Okay, and then the last thing that's important with compound interest is what are we actually compounding it for what amount of time? So our first one we have annually. So if we are compounding it annually, that would be an n value of 1 because I'm only compounding it once per year. So number of times in a year, only once. Next one is quarterly. So every quarter, that's going to be 4 times in a year. So my n would be equal to 4. If I have monthly, that would be compounded 12 times in a year. So n would be equal to 12. And then last but not least, if I have continuously, that's going to switch over to our PERT equation instead. So anytime you see that word continuously, because continuously isn't a number, it's all the time over and over and over again, we switch over to that PERT equation. So we're going to do one together, and then I'm going to let you try some of these on your own. So if we have our annually, let's go ahead and plug everything in. We have A is equal to, which is what we don't know, so A is equal to 500. So 500 for our P times 1 plus R divided by N. So 0.06 divided by N, which is 1. And then raised to the power of N times T. So 1 times 8. And this is all good to go for me to just type straight into my calculator. So I'm going to switch over to my TI-84. And we have 500 parentheses 1 plus, and I'm going to do my fancy parentheses, so alpha y equals, hit that first option, n over d, enter. And then it was 0.06 for rate divided by n, so 1. And this is all being raised to a power of n times t, so 1 times 8. And then I get 796.924, which it is a dollar amount, so 796.92. Not 292. And you might have noticed in this problem, there's some redundancies, dividing by 1, multiplying by 1, stuff like that. I like to always type the equation in its entirety, even if there are some pieces that might feel kind of redundant in terms of what we're typing. But I do always like to type it in all the way and not try to do any math on my own or on the side or anything like that. But that takes care of number 1, y'all. Compound interest is really straightforward. You just plug it straight in for whatever you have. So I want you to go ahead and try and do BCD on your own. Go ahead and pause the video, and then you can check your work here in just a second. All right, y'all. So hopefully you got similar answers to me. So for B quarterly, we're plugging in that 4. We should get 805 and 16 cents. On monthly, we're plugging in that 12 for our N. So the only thing that's changing here is our N. Plugging in the 12, we get 807 and 7 cents. So we can see as we're compounding more times in a year, we're making more money throughout the year, which makes sense because we're adding that interest on to the amount of money that we started with. And then last but not least, continuously, our PERT equation. So A is equal to 808.04, so even a little bit more than our monthly. So going all the way through, all the way to continuously, the more times we compound that interest, the more money we are going to make in the year. So something to consider. Sometimes in finances, you'll see maybe a higher interest rate but lower compounding versus a lower interest rate but more compounding. And so it's good to be able to evaluate which one of those is actually going to be better in the long run versus which one might be better in the short run, because that might help you make a decision on which account you want to invest in. Okay? But with that being said, that's really compound interest in a nutshell. We have one other equation that we're going to talk about today, and that other equation is exponential growth and decay. And exponential growth and decay is really a very similar situation. We have A, we have P, we have R, we have T, but it's a little simpler. We're not having that compound interest. And in this situation, we're either growing exponentially or we're decaying. That growing exponentially means that we are getting bigger, which means we want to be multiplying that initial by something that is greater than 1, 2, 3, 4, 5, or 1.1 or 1.06. So for exponential growth, we want to actually add the R value, add the rate in the equation. For decay, we're getting smaller. We want to be multiplying by something that's less than 1, which was why we subtract the R value for exponential decay. So adding a little extra step in these exponential growth and decay problems, you also have to determine if the situation is growth or it is decay. And so we have some buzzwords, growth. We have increasing, growing, getting bigger, increasing in value. Any of those things would be growth, decay, decreasing, devaluing, depreciating, falling apart, going down, any of those things that will tell you that there's some sort of decay occurring in the problem. So those are kind of the things you want to look out for. So let's look at number 2. Number 2, the population of a small town of 10,000 people is growing at a rate of 5.2% per year. And we want to predict the approximate population 10 years from now. So just like we did with our compound interest, we want to identify some of our key features. So we have 10,000 people, we have 5.2% per year, we have population from 10 years from now, and we have that growing. So some important information, our initial amount is 10,000, so P is equal to 10,000. Our growing, so we do have growth in this situation, so we're going to be adding that R value. Our rate is 5.2%, so that means R is equal to 0.052. And then we want to predict the approximate population in 10 years, so T is going to be equal to 10. And then, of course, what are we actually trying to find? We're trying to find that population. So A is our unknown variable. So just like we did for compound interest, we want to set up our equation. So A is equal to 10,000, 1 plus 0.052. And of course, we're taking that to a rate of T, so to 10. And now we got everything plugged in. We want to go ahead and plug that all into our calculator, just like we did for compound interest. So switching on over to our TI-84, we got 10,000. Gotta move me. We got 10,000 times 1 plus 0.052 raised to the power of 10, which will give us about 16,601. And we do get a decimal, but of course we're talking people here. So you could put a decimal. I wouldn't count it wrong if you put 16,601.88 or 0.89, but I would go ahead and round this to the whole person. So 16,602. And even if you did 16,601, because you're like Mr. Arbona, we didn't actually reach us 16,602nd person. We only have 0.88. 16,601 would also be fine. I'm not really going to be that picky when we're going for these answers here. Okay, but that is growth and decay. Only thing, of course, that would change if it was a decay problem instead would be that subtraction of the R value instead of adding the R value. So pretty straightforward. So I want you to go ahead and try and do 3, 4, and 5 over on the right side of the paper. So for each of them, identify your unknowns, identify your unknowns, identify your knowns, decide if it's growth, decay, maybe compound interest, and then go ahead and plug it into your equation. So go ahead and pause me now, give yourself some time to work those out, and then unpause me when you're done. All right, also just talking about each of these briefly. So number 3, we have the rate and the number of reported cases of robbery is dropping at 7% per year in a given region of the country. The number of cases reported this year was about 156,000, and that number continues to drop at this rate. What will be the predicted number of cases 2.5 years from now? So it is dropping, so we have exponential decay, so we're going to be subtracting that rate. 7%, of course, would become 0.07. Setting it up, we do get 130,116 cases over 2.5 years. Of course, 2.5, that's where we get that 2.5 from for the time. Looking at number 4, suppose that you purchased a car in 2008 for $26,000, and the value of the car decreases. So decreases again, we're talking decay, by 16% each year. How much will your car be worth in 2010? And how much will your car be worth in 2014? So start with 26,000. Rate is going to be 0.16 because we're moving it twice, not 1.6. That would be a little big for an R value. And then this one's a little different. They didn't tell us a T value. They told us the years, so we have to kind of evaluate that. So 2008 to 2010, that would be 2 years. 2008 to 2014, that would be 6 years. Plugging that into the equation once with a time of 2, once with a time of 6, gives us that 18,345 and 60 cents and 9,133 and 75 cents. So different values as we keep going on. Of course, it would keep decreasing if we kept going on in the future. And then last but not least, number 5, the number of bacteria in a colony is growing continuously. The amount at the beginning was 4,500. The bacteria are growing at a rate of 5.5%. We want to predict the amount of bacteria in 4 days. So a couple things. Firstly, we read growing continuously. So yes, it is growth, but it is that continuous compound growth. So we use that continuous formula instead. Anytime we see that word continuously, even if it's not compounded continuously, if it's just continuously, you use the PERT equation. We have that starting amount of 4,500. It's growing at a rate of 5.5%, which gives us 4,500 for P, 0.055 for R, and then predict the amount of bacteria in 4 days. So no, you do not need to take 4 and divided by 365 to multiply by this decimal amount of years. They gave it to us in days. They say it's growing continuously every day. So they've changed the time barrier to be in days. So instead, we're going to plug in 4 as days, and it's 5607 bacteria after a certain number of days as opposed to after a certain number of years. So that's why I said 99% of the time it's going to be years, but if they switch the units up on you in the problem, then those are the new units. You don't have to worry about trying to do some unit conversions. That's not going to be a part of this unit today. Okay, but let's go ahead and finish this out. Let's do 7 together, and I'm going to let you do 8 on your own. So looking at 7, there are currently 489 students at IHS, and if that number is increasing at a rate of 1.8% per year, we want to know when there will be 650 students at IHS. So let's identify our key pieces of information just like we've been doing. So 489, rate of 1.8% per year, and when will there be 650? So this time we're actually given two amounts, 489 and 650. We're given a rate, a percentage. We're not told the time, and instead we're asked when. So the difference here is now T is actually going to be our unknown variable. So T is what we're trying to find here. We have our A value, our final amount. It's going to be 650. We have our P value, our initial amount, which of course would be 489. And then we have our rate, 1.8%. It's going to be a teeny tiny 0.018. And so we can go ahead and set up our equation from here, just like we've been doing so far. So 650 is equal to 489. And then 1 plus, because we are growing, so 0.018. And we're taking it to that T, which is the only piece that we don't know. So T is the only thing we don't know. We know everything else. So now we want to solve for T. And I'm going to solve for T by getting that T out of the exponent. Now we've learned the only way to get rid of an exponent like this, because I can't take a root T, that doesn't make any sense, is I actually have to convert this from an exponential over to a logarithm. We're going to use our hook method that we talked about a week and a half ago. So to be able to do our hook method, we need to have our exponent by itself. Right now, it's got that 489 hanging out in front. So we're going to go ahead and divide both sides by 489 to move it over to the other side of the equation. And even though, yes, I could go ahead and type in 650 divided by 489 into my calculator right now, we're not going to do that because I want to wait till the very end to plug everything into the calculator, because your calculator actually rounds through every step that you do in it. So if you do everything in little small steps, you're technically rounding every time, and you could be skewing your final answer a little bit. So we're going to wait till the very end to type anything in the calculator. So we're going to keep it as 650 divided by 489 over on the left. Then over on the right, all we have left is, I'm going to go ahead and simplify 1 plus 0.018 to just make it 1.018. And that is raised to the power of T. So now our exponent based raised to the exponent, it's all by itself. So I can go ahead and do my hook method, hook my base over to the left side, exponent's going to drop down, and I'm going to end up with this new log-based equation. The log with the base of 1.018, and of course of 650 divided by 489, and that is equal to our t, our time variable. So I have t completely by itself, which means this is what I can now type into the calculator. So we're going to go over to our calculator. And we need a special log function because we need to be able to both plug something into the log and plug in a base. So if we just hit the log button, you can see I can't put anything in for the base right now. It's automatically a common log, which we know a common log. Whenever you don't see a base written, it has a base of 10. I don't want to have a base of 10. I want to have that base of 1.018. So I'm going to hit the math button. I'm going to arrow all the way down to log base, which is a special function. It's option A in the math window that allows me to get a logarithm that has a base that I can put in. So I'm going to put in my base of 1.018. And then on the inside, alpha y equals, get my nice fractions, 650 and divide by 489. Going to go ahead and hit enter because we're all good to go. And it says it's going to take 15.95 years. So 15.95 years is a perfectly acceptable answer. We can have a decimal portion of a year. You could also round it up to 16 years. Either one would be fine. But there you have it, y'all. So that's a little bit of an extra skill, and we could have various different things we could have to solve for. We could have to solve for P instead of A, which would just mean we have to divide over our base and our time variable over to the other side. We could have to solve for rate, which would mean we would take that exponent to both sides. So we could have a couple of different things we could actually have to solve for in these problems. It's not always just going to be plug in all the stuff and get out the A. Sometimes there will be a different unknown that you'll have to solve for. But I want y'all to go ahead and try 8. It's going to be very similar to 7. So go ahead and pause me now, and then you can check your work here in just a second. All right, y'all, let's talk 8. So 8, if you get $3,000 for a graduation gift and invest in an account that earns 2.4% interest compounded quarterly, when will it grow to $5,000? So this is compounded, so we're looking for that end value as well. It's going to be increasing. We don't have to worry about growth or decay with compound interest. So we get an A value, our starting investment of $3,000. We want to know when it's going to get to 5,000. So P is 3,000, A is 5,000. Our rate is 2.4%, so our R value is 0.024. It's being compounded quarterly, which means our N is going to be 4. And when will it grow to 5,000? So time is our unknown. So we set everything up. We get 5,000 equals 3,000 times 1 plus 0.024 divided by 4 and raised to that power of 4 times t. So t is still our unknown variable up there in the exponent. So we go ahead and divide 3,000 on both sides. We get 5,000 over 3,000. Inside the parentheses, I simplify it to 1 plus 0.006 because 0.024 divided by 4 is 0.006, which of course I did say we don't have to do any math beforehand. So if you want to leave your base as 1 plus 0.024 divided by 4, by all means. But I do like to do some simple math where really I know, like I'm not losing a decimal by dividing 0.024 by 4 to get 0.006. Then once we get to that point, we go ahead and do our hook method, shifting our base of our exponent over to the other side to become a base of the log. So we get log base 1.006 of 5,000 divided by 3,000, and that's equal to 4 times t. So extra step this time, instead of it being equal to just t, it's equal to 4 times t. So we had to add in the step of dividing both sides by 4. And of course, I can't divide the base of my log by 4. I can't divide the inside of my log 5,000 over 3,000 by 4. So it's really still that log base 1.006 of 5,000 over 3,000. And then I'm just going to be dividing all that by 4 there at the end. So plugging it into our calculator, we do get about 21 years. If you got 21.53, that is wrong. It is 21.35. So if you got 21.53, you might have done something a little bit off because, of course, 21.5, you would think that would be 22 years. But it is 21.35. A couple other things to remember. Remember, anytime we're doing our log, y'all, we have to move that p over to the other side first. We have to have that base by itself to be able to do our hook method. And then, of course, make sure if you are dividing like that, that you don't divide inside the logarithm. It's protected just like a square root or just like a set of parentheses to an exponent. We can't divide on the inside of the logarithm, so we're just going to leave it as that divide by there at the end, y'all. But that is applications of exponential and logarithmic functions. There's a lot more that we didn't necessarily go over today that you might encounter on the review or on the practice, so definitely still keep an eye out for those. And, of course, come in and ask questions if you have any, y'all. Thank you.